Before you finish watching this sentence, you will have traveled thousands of kilometers through space. Not because you're on a rocket, not because you're flying in an airplane, but because the ground beneath your feet has never stopped moving. At this very moment, Earth is spinning at up to 1,670 kilometers per hour. It is racing around the sun at more than 107,000 kilometers per hour. Our entire solar system is orbiting the center of the Milky Way galaxy at roughly 828,000 kilometers per hour. The Milky Way itself is falling toward neighboring galaxies, while the universe continues to evolve on scales so enormous that even light struggles to cross them within billions of years. Every second of your life, you are taking part in one of the fastest journeys imaginable. Yet your coffee doesn't shake. The air around you doesn't roar past your face. You don't feel the slightest hint of movement. How can a planet moving so unbelievably fast feel perfectly still? To answer that question, we'll have to challenge one of the oldest assumptions humans have ever made. We'll discover why standing still may be nothing more than an illusion, why the universe has no preferred place of rest, and how one deceptively simple question eventually led to some of the greatest discoveries in the history of physics.
Along the way, we'll leave Earth behind, travel through our galaxy, explore the largest structures ever observed in the cosmos, and uncover a surprising truth that even today continues to shape our understanding of reality. So let's begin with something that seems completely obvious. Right now, you probably feel motionless. Perhaps you're sitting in a chair. Maybe you're lying on a couch, standing in a room, or riding on a train. Whatever you're doing, your senses are giving you a clear message. You are at rest. That feeling is so convincing that we rarely question it. From the moment we're born, our brains learn to associate movement with sensation. When a car suddenly accelerates, we feel ourselves pressed back into the seat. When it brakes sharply, our bodies lurch forward. A fast elevator makes us feel heavier for a brief moment before the sensation disappears. An airplane during takeoff pushes us firmly into our seats, while turbulence reminds us that the aircraft is changing its motion. These experiences seem to teach a simple lesson. If something is moving, we should feel it.
But that lesson contains a hidden mistake. What we actually feel is not motion. We feel changes in motion. That distinction may sound subtle, but it is one of the most profound ideas in all of physics. To see why, imagine stepping aboard a luxury cruise ship. The sea is unusually calm. The engines are remarkably quiet. There are no waves, no vibrations, and no visible windows. You're inside a beautifully furnished cabin with no view of the outside world. A glass of water sits on a table. A butterfly flutters gently through the room. You toss a coin into the air. It rises, pauses for an instant, then falls straight back into your hand. Everything behaves exactly as you would expect. Now imagine that without your knowledge, the ship begins moving across the ocean. Not with a sudden jolt, not with roaring engines. Instead, it accelerates so smoothly that after reaching a constant speed, every vibration disappears. The ship is now gliding across the sea at hundreds of kilometers per hour. Inside the cabin, what changes? Surprisingly, nothing. The butterfly still flies normally. The glass of water remains undisturbed. The coin still lands in your hand. You can jump, walk, write, eat, or play a game of chess exactly as before. Without looking outside, there is no experiment you can perform that reveals whether the ship is standing still or moving smoothly at constant speed. That conclusion feels almost impossible. Surely moving hundreds of kilometers per hour must leave some clue. Yet nature says otherwise.
More than 400 years ago, this simple observation became one of the turning points in the history of science. The Italian physicist and astronomer Galileo Galilei realized that motion is far stranger than common sense suggests. During Galileo's lifetime, many scholars still accepted ideas inherited from the ancient Greek philosopher Aristotle. According to Aristotle, the natural state of objects was rest. Continuous motion seemed to require a continuous force. If something kept moving, something had to keep pushing it. At first glance, that idea seems reasonable. Roll a ball across the floor, and it eventually stops. Push a box across the ground, and it quickly comes to rest. Throw a stone through the air, and it eventually falls. Everyday experience appears to support Aristotle's view. But Galileo noticed something important. Those objects weren't stopping because motion naturally dies away. They were stopping because of friction. The floor resists the ball. The ground resists the box. The air resists the stone. Remove those resistive forces, and something remarkable happens. Motion doesn't fade. It continues. This insight was revolutionary because it separated what humans experience from what nature actually does. Our world is filled with friction, air resistance, collisions, and countless tiny forces that constantly slow things down. Because we live surrounded by these effects, our intuition developed around them. We mistake friction for a fundamental property of the universe, when, in reality, it is only one influence acting within it. Galileo imagined ideal situations where friction became negligible. In those situations, an object already in motion had no reason to stop. It would simply continue moving forever at the same speed and in the same direction. This idea became known as inertia. Decades later, it would form the foundation of Sir Isaac Newton's first law of motion. Newton expressed it with extraordinary simplicity. Every object continues in its state of rest or uniform motion in a straight line unless acted upon by a net external force. Notice what this law quietly tells us. Rest and constant motion are placed on exactly the same footing. Physics makes no special distinction between them. An object sitting motionless on a table and another drifting through empty space at thousands of kilometers per second obey precisely the same law. Without something external changing their motion, both states are equally natural. That single sentence overturned centuries of intuition. It also raises a fascinating question. If constant motion is physically indistinguishable from rest, then what does it actually mean to say something is moving? Moving compared to what? Imagine floating alone inside a spacecraft far beyond the edge of our solar system. No nearby planets, no visible stars, no engines firing, no vibrations, no windows. Perhaps your spacecraft is drifting at 1 kilometer per second, or 100 kilometers per second, or 1,000. Inside the cabin, every experiment gives the same result. A ball thrown upward returns to your hand. A pendulum swings normally. A drop of water floats exactly as expected. There is no internal instrument capable of revealing your constant speed. That sounds unsettling because we're accustomed to believing that speed is something absolute. Our cars have speedometers. Airplanes display airspeed. Spacecraft report velocity. Surely speed must be measurable? It is, but only relative to something else. Your car's speedometer measures how fast you're moving relative to the road. An aircraft measures speed relative to the surrounding air. A spacecraft measures velocity relative to a chosen reference frame, such as Earth, the Sun, or distant stars. Remove every external reference, and the very concept of speed begins to lose its meaning. This is one of the deepest lessons in physics. The universe does not provide a giant cosmic signpost labeled perfectly still. Instead, every measurement of motion is a comparison. Earth moves relative to the sun. The sun moves relative to nearby stars. Those stars move relative to the center of the Milky Way. The Milky Way moves relative to neighboring galaxies. Even those galaxies move relative to even larger cosmic structures. Every level of the universe is in motion relative to another. And that realization leads us to an extraordinary possibility. Perhaps the reason Earth feels perfectly still is not because it isn't moving. Perhaps it's because every single thing around us is making exactly the same journey through space.
For thousands of years, people naturally assumed that Earth must be standing still. It wasn't simply because they lacked telescopes or mathematics. It was because every human sense seemed to support that conclusion. Stand outside on a calm day, and nothing appears to move beneath your feet. Mountains remain fixed on the horizon. Trees grow vertically rather than leaning backward. A bird can build its nest on a branch without compensating for Earth's incredible speed. Clouds drift gently across the sky instead of being swept thousands of kilometers behind the planet. If Earth were truly moving, as modern astronomy claims, surely someone should notice. The remarkable thing is that these arguments are not foolish at all. In fact, they are exactly the questions a careful observer should ask. Science advances not by ignoring obvious objections, but by answering them. One of the earliest people to confront this puzzle systematically was Galileo Galilei. By the early 17th century, the idea that Earth orbited the Sun, first proposed by Nicholas Copernicus in 1543, was still deeply controversial. Critics repeatedly asked the same question. If Earth is moving, why don't we feel it? Galileo understood that the question itself contained an assumption that had never been tested. It assumed that motion should always be directly detectable. But what if that assumption was wrong? To answer this, Galileo introduced one of the most influential ideas in the history of physics, the principle of relativity.
Today, the word relativity immediately brings Albert Einstein to mind. But long before Einstein transformed physics, Galileo had already uncovered a simpler form of the same principle. He argued that all experiments performed inside a system moving with constant velocity must produce exactly the same results as they would if that system were completely at rest. This wasn't merely philosophy. It was a statement about the laws of nature themselves. Suppose two observers each have an identical laboratory. One laboratory sits on the ground. The other is inside a spacecraft, drifting smoothly through deep space. Each observer performs hundreds of experiments. They swing pendulums, drop metal spheres, measure chemical reactions, study the behavior of light emitted from ordinary lamps, watch insects fly inside glass containers, observe water flowing through narrow tubes. Every experiment produces identical results. Neither observer can claim to be truly stationary. Neither laboratory possesses a privileged state of rest. Physics itself refuses to distinguish between them.
This concept is so deeply embedded in modern science that it has become almost invisible. We rarely stop to appreciate how extraordinary it really is. Imagine if the universe worked differently. Imagine if there truly existed a universal state of absolute rest. Every laboratory could simply compare itself against that invisible cosmic frame and immediately determine its exact speed through space. Different physical laws would operate depending on how fast you moved. A pendulum might swing differently. Atoms might vibrate differently. Chemical reactions could change. Entire branches of physics would depend on your absolute velocity. Nothing like this has ever been observed. Every experiment ever performed tells the same story. Nature does not reveal an absolute state of rest. Instead, every measurement of motion depends entirely upon what you choose as your reference. This seemingly abstract idea becomes surprisingly familiar once we begin looking at everyday life. Consider two passengers seated on a high-speed train moving at 300 kilometers per hour.
One passenger gently rolls a tennis ball across the table toward the other. From their perspective, the ball moves at only a few kilometers per hour. Now imagine an observer standing beside the railway tracks, watching through the window. To this observer, the ball is not moving at just a few kilometers per hour. It is moving at approximately 303 kilometers per hour. Neither observer is wrong. They are measuring different velocities because they occupy different reference frames. Velocity is not an intrinsic property of the ball. It is a relationship between the ball and whoever is measuring it. This principle applies everywhere. A person walking inside an airplane, a satellite orbiting Earth, Earth orbiting the Sun orbiting the Milky Way, even galaxies themselves. Every motion in the universe is measured relative to something else. This raises another question that is even more profound. If every object can only be described as moving relative to another object, then what exactly is space itself? Does space provide the ultimate background against which all motion occurs? For centuries, many scientists believed it did. Isaac Newton imagined something he called absolute space.
Although invisible, Newton believed absolute space existed independently of matter, acting as a fixed stage upon which every event in the universe unfolded. According to this picture, planets moved through absolute space. Stars moved through absolute space. Light itself traveled through absolute space. Even if no observer existed, Newton believed the universe would still possess a definite objective state of motion. It was an elegant idea. It also seemed perfectly reasonable. After all, if motion is real, shouldn't there be something that objects move through? For more than 200 years, absolute space remained one of the central assumptions of classical physics. Then something unexpected happened.
During the 19th century, physicists made enormous progress in understanding electricity and magnetism. James Clerk Maxwell united these seemingly separate phenomena into a single mathematical framework, now known as Maxwell's equations. These equations predicted something astonishing. Light is an electromagnetic wave. Even more surprising, the equations predicted that electromagnetic waves always propagate through empty space at the same speed, approximately 299,792 kilometers per second. This immediately created a mystery. Every known wave requires a medium. Ocean waves travel through water. Sound waves travel through air. Seismic waves travel through rock. So, what medium carries light? Scientists proposed the existence of an invisible substance filling all of space. They called it the luminiferous ether. According to this idea, the ether was everywhere. Planets moved through it. Stars drifted through it. Entire galaxies passed through it. If Earth really orbited the Sun at nearly 30 kilometers every second, then our planet should constantly experience an ether wind, much like a cyclist feels air rushing past while riding forward. That invisible wind should slightly alter the measured speed of light depending upon Earth's direction of travel. It was a beautiful prediction because it could be tested. In 1887, two American physicists, Albert A. Michelson and Edward W. Morley, built one of the most precise scientific instruments ever constructed at the time. Their goal seemed straightforward.
Measure Earth's motion through the ether. The experiment used an instrument called an interferometer. A single beam of light was divided into two identical beams traveling at right angles to one another. After reflecting from mirrors, the beams reunited. If Earth were moving through the ether, one beam should take slightly longer than the other. The tiny difference would shift the interference pattern produced when the beams recombined. The predicted effect was incredibly small, but Michelson's instrument was sensitive enough to detect it. They repeated the measurements. Again and again. At
different times of day.
During different seasons, as Earth occupied different positions in its orbit around the Sun. Nothing. No ether wind, no measurable shift, no evidence that Earth was moving through any invisible medium. At first, many physicists assumed something must be wrong with the apparatus. Surely the ether existed. Perhaps the experiment lacked sufficient precision. Perhaps Earth somehow dragged the ether along with it. Perhaps some unknown physical effect concealed the expected result. For nearly 2 decades, increasingly elaborate explanations were proposed to rescue the ether hypothesis. Yet every new experiment produced the same unsettling conclusion. Nature stubbornly refused to reveal any preferred frame of rest. The failure to detect the ether became one of the greatest scientific mysteries of the 19th century. It was not merely an experimental inconvenience. It challenged one of the deepest assumptions underlying classical physics. If there was no universal background filling space, if Earth could not detect its own motion through the cosmos, if every observer measured the same laws of physics, regardless of their uniform motion, then perhaps the universe itself was fundamentally different from anything Newton had imagined. Gravity was not just the force that held the apple in place or kept the moon circling Earth. It was also the invisible thread tying all motion together. Yet even with Newton's brilliance, something still nagged at the edges of his equations. Why did gravity act so subtly on Earth's motion, never jarring us with sudden jolts? And if gravity bound us, what if motion wasn't a property of an object, but a relationship, one that stretched beyond Earth, beyond the solar system, into the very fabric of space-time itself? This is where the story turns. In the early 20th century, a young patent clerk in Switzerland, Albert Einstein, began to question all of this. What if the speed of light wasn't just a number? What if it was a cosmic speed limit? What if space and time were not separate stages, but woven together in a single fabric?
Einstein's special relativity didn't just explain why light was constant. It revealed that motion, rest, and time were part of a grander unity. Suddenly, the idea of a cosmic speed limit shattered the Newtonian stage. If no universal stillness existed, then Earth's motion, the sun's motion, even light's motion, these were all relative. Every observer, whether in a train or a spacecraft, saw the same laws unfolding because the universe itself conspired to keep them hidden. And as we stand back now, we see that every galaxy, every distant quasar, every speck of stardust, all of them move, all of them dance, but we never feel it. So what does it mean to move? Is it just an accident of perspective? A cosmic choreography that never needed a center? Perhaps motion is not a property of things at all, but a relationship that unfolds as part of space-time itself. And so, just as you began in your chair, still and unaware, by the time we finish, you will have traveled further than you ever imagined, and all without leaving your seat.